Hello everyone, this is Hussein Haydari and we're going to continue our discussion on polymers, specifically polymer structure and shape that we started from the second lecture of this series. Today we're going to start back from copolymers and how polymers are cross-linked together, and then we're going to talk about crystallinity and percent crystallinity or degree of crystallinity, and then we're going to talk about another classification of polymers based on their properties, their material properties. So the last thing that we discussed in the previous lecture was how these polymer chains could be cross-linked laterally rather than longitudinally and along the main polymer backbone, but rather between these chains. So we have these primary bonds that between monomers, and then we have these secondary bonds that can actually connect these long strands, these long polymeric chains together. So what you see here is that you've got a cross-linked set of chains that have actually got lateral bonds that are also covalent bonds, as well as the covalent bonds that connect the main backbone of this structure. So if this is organized to a degree that you can see some sort of repeatability, it's more of a network structure or a crystalline structure, as we will see in a minute. So as you can imagine, as we go from these sliding chains to chains that are branched and can somewhat get entangled with each other much easier, to chains that are cross-linked together and networks, the strength will increase. Here we're talking about the mechanical strength, the ultimate tensile strength. So will the stiffness of these polymers. As we move to the right, you'll have stiffer matrices. As we move to the left, you'll have lower stiffnesses. And then we briefly discussed the end-to-end distance. It's a topic of rather complex computation if you want to figure that out for a variety of polymers. Depending on the way they come to equilibrium, these angles and these chains, basically the monomer angle and the conformation that we discussed earlier, can make it very complex to calculate how long this end-to-end distance is. So although you can derive simplified equations to calculate this, we will ignore that because in the real case, it can be a lot harder. In class, I will give you a brief example of how you would do that, but it's not something that we would be focusing on, or you'll be asked for the exam. So the next thing that we discussed was copolymers, the concept of having more than one type of monomer in your backbone. And what you see here is examples of how this dual or even 3 or 4 types of different monomers could be incorporated within the same polymer matrix. In this case, you have a random configuration where you have a couple of each monomer followed by a couple of the other. In this case, you have an alternating situation where you have one of A and one of B, followed again by another one of A and another one of B. And so the monomer blocks, basically, the monomer units are basically connected after each other. In this case, you've got blocks of each monomer, followed by blocks of the other monomer. So this scenario and the graft scenario, which is the scenario where these side branches are completely made out of the secondary monomer, These two happen usually when you've synthesized one type and then you mix it in with another type and you then cross-link it again, or basically you continue the polymerization. And so what happens is that you've got chunks or chains of one type that are already made and are trying to stick to the other type. So now that we've discussed copolymers, we're going to talk about crystallinity. So in general, crystallinity is a rather intricate topic. The reason is that it's difficult to define the crystalline unit. So you actually have to figure out what that smallest unit for your crystallized structure is. And so in this case, it's even harder because with polymers, you've got all sorts of different lengths, all sorts of different molecular weights. So it's difficult to detect sort of a common repeating unit, but still a lot of these polymers do exhibit repetitive patterns. If you look at the structure carefully, you can see some repeats. So if you can detect these repeats in your structure, that means that you've got some sort of a crystal unit. In this case, you can kind of see that. It's a bit difficult to detect. I'll try and show some 3D models in class to actually make it easier to understand. But basically what you see is that this particular unit here, if these chains are all parallel to each other, you can take this slice of it, and because of the force fields, they've got some sort of a repeated relative position and orientation with each other. You can see how this slice of this is repeated again up here and so on and so forth, in which case you can see this angle here, they're all facing that direction, and so it's going to repeat up here again. So it's basically the same repeat structure. Now, if, for instance, there was something in between, if there was a branch popping out of this, it would have completely eliminated this crystalline form. So it's very rare that you have a fully crystalline polymer. So in fact, it's a matter of the degree of crystallinity. So they can be all the way from 0% to close to 100% crystalline. So this is what I was talking about. Again, an example here is that you see all these chains wiggling up and down. So you can see this sort of a serpentine behavior here. And then if you took a cross section of that, and you can imagine that there could be units of this repeating up there, you could see some sort of organization and order. So it's somewhat resembling of a crystal structure, although quite different from the conventional idea that we see, for instance, in solids, like metals, for instance. In metals, what you have is a perfect atomic crystal. And in this case, you've got a secondary crystal. So they've already formed these molecules, these rather large macromolecules, and these molecules are now being configured in space so that they actually form a crystal. So it's basically the intermolecular bonds and connections that define the crystal. So as I mentioned earlier, percent crystallinity is something relevant for polymers because they're either they're somewhere between 0% and close to 100%. They can't be 100% because that's too perfect. I can't imagine that. I can't say it's impossible, but it would require some very highly controlled synthesis environment. So in the typical cases, you have a percent crystallinity which is what I'll define in a moment, going to tell you exactly what the strength of the material and the stiffness are, because as it's more, as it gets more crystalline, it's going to have a higher tensile strength. Here, TS represent tensile strength, that's mechanical tensile strength, and E modulus, or elastic or Young's modulus. So they're going to get stiffer and they're going to be stronger as you increase their degree or percent crystallinity. So another way that you can increase percent crystallinity, apart from the synthesis process, is by doing annealing. So other than controlling your synthesis environment, you can do secondary processing on your polymer, including annealing, thermal annealing, to obtain a higher degree or percent crystallinity. So this is sort of a schematic of what that looks like. You have a structure, a lot of the regions it's going to be amorphous, and a lot of the regions you're going to have crystallinity at a high level. So you've got both crystalline regions and amorphous regions. So it's a mixture of these two. If the dominant part of this is the crystalline part, then your percent crystallinity is going to go higher. If your dominant part is your amorphous region, then your percent crystallinity is lower. So you can see that it's going to be a formula that has both of these in it, the amount of the crystalline regions and the amount of the amorphous regions. But it actually goes down to this formula, which takes in the density. So I'm going to explain what this means right now. So if you've got a sample that you've taken out of your synthesis chamber, so let's say they give you a sample, it's an unknown sample, they just synthesized this sample, and you don't have access to look at images of the structure and to basically derive that. So what you do is you look at the density. So rho S here is the density of your semi-crystalline structure that they've given you. And then you know the density for the fully 100% amorphous, rho A, and you also know the density for the fully crystalline, rho C. So if you know the density, if this was fully crystalline, and you also know the density if this was fully amorphous, and you're able to measure your density, the density of your sample that you've been given, you can actually figure out what the percentage is. Now, why is this the case? Because as you can see, if you make this more and more amorphous, or in other words, if you make it more and more crystalline and organized, the density is going to go higher because you're going to get a much better packing. If you make it amorphous, the packing is a lot less compact as it's amorphous and random, and so the density is going to go down. If you make it crystalline, what's going to happen is it's the best, most tightly packed structure, so you'll have minimum volume, or in other words, maximized density. So this is exactly why we use density as our metric. So for example, here is a good example. They give you a sample that's 1.21 grams per centimeter cubed of density. And you know that the amorphous has a density of 1.1 grams per centimeter. And the perfectly crystalline has 1.34 grams per centimeter. Please observe that the perfectly crystalline has a lot higher density than the amorphous. And the reason again is that it's tightly packed, compacted into this organized lattice. So now that you've got your density, your sample density here, you can plug it into this formula. And what you get is you've got the density of the fully crystalline, you've got the density of your sample minus the density of the amorphous, divided by the density of your sample times the density of fully crystalline minus the density of amorphous. Multiply that by 100 and you'll get approximately 51%. So your sample here has about half of its volume, these crystalline regions, and half of its volume occupied by these amorphous regions. So it's a half-half blend of both of these. This is what this result here is telling us. Okay, wonderful. So it's really difficult to get a single crystal, meaning that your structure is entirely crystalline. As I mentioned, you usually get a mixture. So you have an extreme case where you get a single crystal, meaning that the entire material you've got has become a single crystal, a crystalline structure. On the other end, you've got spherulites, which are very fast-grown structures. Basically, what happens in these cases, and if you look at the synthesis of these, it's beautiful. You have a nucleation site. It maintains some level of crystallinity that propagates from the nucleation site, but then outside there are regions of amorphous material connecting these tie molecules, as they call them, the amorphous regions connecting these crystalline regions together, these crystalline branches. And what you end up getting is these localized nuclei that actually locally induce some crystallinity. And then once they reach the other site, which is the boundaries of another nucleation site, it actually forms its own grain structure. So what's happening here is that you initially form a lot of these nuclei, and then each of these grow out and branch into these basically into these crystalline structures. Unfortunately, they cannot occupy the entire region, so there are going to be some branches, and there's going to be some tie molecules of amorphous material, and then these nucleation sites somehow reach each other in the middle, which is the boundary of these grains. And each of these we call a spherulite grain, which starts from its center, from the nucleation site, branching all the way to the boundaries. Okay, so this is all we're going to cover on crystalline structures and crystallinity, but there's a lot more going on with how this translates to mechanical properties, and there's a lot more depth into how these branch structures densify and how you can actually sort of predict the density of these structures. But we're going to leave it here as an introductory discussion. So the last piece of information we're going to add lecture series for this week is thermosetting versus thermoplastic polymers. Now, the names sort of give away what this classification means, but the idea is that a lot of these polymers, when you heat them up, or in other words, introduce some thermal energy, you can actually melt them and reform them, and they will stay in that state. These materials are called thermoplastics. A good example for these is these plastic bags. If you heat them up, you'll see that they start deforming, or these Lego blocks. If you heat them up, they're going to completely go out of their original shape, and you have to heat them up to a temperature called the glass temperature, the glass transition temperature, at which point they actually go from this brittle plasticky feel to sort of a molten plastic feel, or not really molten, but more of a gooey sort of look. And so you can then compress them, mold them into a new shape. And in other words, when you heat them, you can reshape them, reform them into a different shape. And this is done at a reasonably low temperature, meaning that you don't need to go all the way to 200 C to do this. You can do it at 70, 80. In a lot of these conventional polymers that we introduce, this is the case, like in polystyrene, in PVC. But a lot of these plastics or polymers are actually thermosetting. So what that means is that you cannot simply heat them up and remold them into a different shape. For example, resins that you cast and cure using light or using temperature, they actually keep their shape, and the shape that is set during polymerization is rather permanent. And you can melt them, but you require excessive heat and temperature to actually be able to melt them down and actually change their shape. So a lot of the utensils and tools that you use in the kitchen that actually go through these higher elevated temperatures do require to be thermosetting. And the reason is you want to maintain that dimensional stability. You don't want them to reshape every time that you heat them up to 70, 100 C. And the tires of your car, you can imagine the huge amount of friction they have to basically resist when driving. So these have to also maintain their shape through these extreme conditions. So vulcanized rubber, a lot of the epoxies, resins that you cast, polyester resins, they're all thermosetting materials. And so basically, there's a distinct difference between these two, which is the trend in which they can maintain their shape, or they actually can lose it easily at rather low temperatures. Now, the reason why this happens, we will get into that when we study the mechanical properties of these polymers in the next set of lectures for next week. We will get into that. We will try and look briefly at how the molecular structure is contributing to this rather interesting behavior. But let's leave it there for this introduction, and we will continue on in the next lecture. Have a wonderful rest of the day, and I will see you in class. Take care.